So, let's say the last talk is by Thomas Ray. We will talk about the residual equilibrium schemes for some nonlinear PDEs.
Thank you for the introduction. Thank you for the invitation to organize it. It's been a great pleasure to be here. And I was invited, I said yes immediately because I really like Ferrara. But then I saw the title of the workshop, and then I was well, I accepted, but should I have things to tell you about hyperbolic balance law and residual? I'm more of a Boltzmann guy, and to me Boltzmann is not exactly hyperbolic balance law, and it's related. So, okay, it could be related problem, but I wanted to be really in the workshop. So I decided to present you this result, which is very recent result with Lorenzo. It's the preprint is not even available. Perhaps some of you already saw this talk because Lorenzo gave it in Cortona, I think, this summer at NAMI. But I don't know if some of you were there. So perhaps for some of you, you already heard about this, but it's still kind of new. And actually, the preprint is finished, and I think we're going to put it on archive at the end of the week of here, Friday. So it will appear in an archive in the next couple of weeks, but still it's not published, it's still preliminary. So, okay. Anyway, so my goal is, our goal here in this work is to provide a simple way, let's say, very non-intrusive, to have schemes which preserve the equilibrium for nonlinear PDEs. Okay. So this residual equilibrium business is really about, so you have a scheme which is high order, which is positivity preserving, total variation diminishing, anything you want, DG, final ideological difference, and spectral method elements. Well, you have in your scheme, but it does not preserve the large time behavior of the equation, for example, preservation of equilibrium. And we want a way to preserve this equilibrium without touching a lot at your scheme, because you like your scheme and you don't want to implement something because you're lazy. So this was kind of our goal with this work. So we tried to be the more general as possible, and so this is the kind of equation that we can deal with up to now, but there will be some follow-up, and I'm pretty sure that it can be extended to a very large class of equations. So, okay, so as I told you, I want to develop schemes, high orders, which well balanced, let's say, so which preserves non-trivial stationary solution, equilibrium solution. So the typical class of equation which have this kind of non-trivial stationary solution are convection diffusion equation. So you have a competition between convection, possibly nonlinear, and diffusion, also possibly nonlinear. So hyperbolic balance law, of course, you have competition between the source term and a hyperbolic system, or even kinetic equation. Even if in that case it's not exactly a competition, because in this kind of equation it's usually the collision part which has some non-trivial equilibrium, which are local in the velocity space, which are localized in the time and physical space, and which are just stationary in the velocity space. And so here there is not really a competition between the two terms, because let's say the transport term doesn't see the global equilibrium. So but anyway, so our approach also applies to this kind of equation, kinetic equation, Boltzmann-like kinetic equation. So yeah, I told you there is a competition between balancing between the different terms in the PDE. So, well, as all of you know, you must know much better than I do, because at first I'm a kinetic guy, a Boltzmann guy, so I discovered the system later on. So well, some example of such equation. So if you speak about hyperbolic system of balance laws, for example, shallow waters, for convection diffusion for media, or hydrodynamic model for semiconductors. Hyperbolic balance laws, there's traffic flow models, and as I told you, kinetic equation, typically what we want to deal with is either the easy case, with say Fokker-Planck, or the difficult case, so Boltzmann or Boltzmann-like for flocking and stuff. And well, the first model which applied to biology, economy, sociology, was about the whole body of each culture of this, and I know that all of you know this very well. So, well, told you, my goal is to develop a high-order scheme which preserves the large-scale behavior of these models. So, as you may know, so the construction of numerical schemes which preserve this stationary solution so can be very difficult. And actually, it depends on the problem. On the particular problem, we have seen that in almost every talk before mine. It's if you want to do a well-balancing business, you have to consider the equation you deal with, and to know the mathematical property of the equation. For example, for kinetic equation, so you want to preserve the steady state, as I told you, only of the collision operator, because the transport part, since the steady state are global in space, so to be ignored mostly by the transport part. So yeah, so you want to compute essentially Gaussian profile for Boltzmann or power laws if you deal with granular media, with a drift term or socioeconomy or economy system with Pareto text. And so everything is related to the velocity discretization, so what you do to treat the collision operator. And well, what people usually do is they want to preserve the mathematical property of the operator, which means conservation of mass, momentum, kinetic energy. You tell me how much conservation you have, and of course dissipation of the entropy. So usually this operator came with an entropy structure, and we want to preserve this as a numerical label. And this is usually what is difficult. Preserve the entropy property of the dynamic collision conservation is manageable. Having dissipation of entropy can be tricky. So okay. So for balance law, and again I know that all of you know this much better than I do. So there is a very large body of literature, and okay, so I gave you the very recent review paper in the reference that deal with this kind of problem very, very well, so I won't spend a large time on this, but yeah, you want to capture the balance between the transport term and the right-hand side, and yeah, so you need to construct suitable numerical fluxes in space. And then for convection diffusion, the first problem. So to me, I mean, to my opinion, and perhaps I'm wrong on this because it's not also not exactly my topic. It seems to me that if you want to preserve the large-scale behavior, you need your scheme to be compatible with some type of gradient flow structure which is built in the equation. So again, you want to preserve the real mathematical property, and this is again related to the conservation of some entropic structure built in the equation. And my opinion, it's very difficult, to my knowledge, it's very difficult to do this. And there's a very recent paper, actually, where the author tried to tackle this problem, where they really, instead of solving the equation and solving all the different terms in the equation, they really write the equation as a gradient flow and try to solve the gradient flow. But then, as some of you may know, you need to compute some very strange norm. You need to compute passage time distance, and that can be also tricky. So, our goal, perhaps it's a long introduction, but our goal with the answer was, well, all this is difficult, all this is related to the type of problem, and we wanted to know that perhaps we can do something which really is more general and it's not that much related to the mathematical property of the equation. So, I will present you, so that will be the main part of my talk, where our idea came from, and so what we did with more general classical equation, and then some evaluation that we did since I think for the last talk, and then yeah, some final consideration. So the idea we had came really from the Boltzmann point of view, I mean from the kinetic point of view, and so it first came from Boltzmann, but then actually it's easier to consider this with the linear equation, so Fokker-Planck equation. So here, space homogeneous Fokker-Planck equation. So here the equation, just to explain you our idea, here is the equation, so it's evolution F, here is probability density, which depends on t the time, and v the velocity of the particle, and so it evolves according to this law. So it's actually a convection diffusion equation. We have linear diffusion and drift terms, okay? So you have drift which try to concentrate the particle, and the diffusion which try to spread the particle, and you have a balance between the two phenomena. And then what happens in large time is that you have equilibrium, which are actually Gaussian distribution. I mean, it's just a heat equation that you rescale here. You take your favorite heat equation, you change the scaling velocity and in time, and you obtain this equation. So of course you have Gaussian distribution, so the heat kernel is related somehow to the heat kernel. Well, and so you want to develop schemes which preserve this large time behavior, because you have an entropy structure here on this equation, and those at one time goes to infinity, the entropy, the relative entropy goes to 0, and the 0 of the entropy is exactly the Gaussian distribution, so you have exponential convergence to Gaussian. And so you want schemes which preserve this equilibrium state. So if you do the easiest thing possible that I can think of, which is central difference, it's really bad but you can do this, you won't resolve the Gaussian distribution. The equilibrium you will obtain is very, very far from this actually. It's very bad. And if you want to have the correct solution, you need to do some more tricky methods such as the Chain-Cooper method, which there is from the 70s, but has not been that much improved since the 70s, because it's quite difficult. You need to rewrite the equation as almost a gradient flow actually, and to discretize the equation on the gradient flow, and you need to actually to know the Gaussian distribution, because at some point you will plug the equilibrium in the method. And if you want to go to nonlinear Fokker-Planck or higher order, so this is order 2, and if you want to go to higher order, it can be really tricky. So a bit of literature on this. But yeah, it's tricky. So here is what we did. So our idea was to use the so-called micro-macro decomposition of the Boltzmann equation. So and the term micro-macro was introduced by Liu and Yu in this very well-known paper, but the idea was older, okay, serious knowledge, and it was the first time that the term appeared. And it's really easy. So you have an equation and you know which is linear, or at least polynomially, where the nonlinear probability is polynomial, or quadratic actually, because it's for Boltzmann first. And so you know the equilibrium, and what you will do is some kind of perturbative argument. You decompose your solution F as the equilibrium plus the perturbation. But you don't want the perturbation to be of order epsilon or something or some small parameter. You just want the perturbation to be a solution to a new equation that you will obtain when you plug this expansion on the original equation, and you want just your perturbation to have 0 moment, so first, second, zeros, first and second moment to be 0. So that when you will do the sum, I mean F will have the correct moment. So here, if you do this with the Fokker-Planck equation, which was here, well, by linearity, of course, since F is G plus M, L of M is L of G plus L of M, and since M is an equilibrium of the operator, you have that L of F is L of G. Also good. And so, since M is time independent, it's a global Maxwellian, so when you time differentiate this equation, the dNdt disappear, and what you have for G is that dG dt is just L of G. But, so it's the same equation. So my original equation was dNdt equal to L of F, and here is dG dt equal to L of G. But here the only difference is that your G has 0 mass, 0 momentum, and 0 kinetic energy. So you solve the same equation, but not with the same initial condition. And because of these 3 property on the moment, what you have is that the only equilibrium of this equation with this constraint is that G equal to 0. No, perfect. If you want a method which preserves the equilibrium, that's perfect. Instead of having to find a way to compute the approximate solution and that your grid will be compatible here with Gaussian distribution, well, you just need a grid which is compatible with constant, with 0. And to my knowledge, every numerical method can do this and solve the constant. So, well, to solve the equation of F, now let's solve the equation on G. Because with any grid, you will be able to find a numerical method such as that if LH is your discretized operator, while LH of 0 will be 0 with, you can do this then with high order. And once you solve this on G, you can recover F just by doing G plus N. And that's it. And okay, as I said, F and L of G at the numerical level is an equivalent because the initialization is different. And moreover, actually, when I say to you that we wanted something which is not intrusive in the way that if you have a code which works well, you want only a tiny amount of modification of your code to another method, is that we can also rewrite this in another way. So now if you have your semi-discrete scheme, you have your code, okay, so semi-discrete in space, and well, as I told you, it does not preserve the equilibrium state because it's not here. For example, the Gaussian won't be compatible with, say, piecewise polynomial spaces, but you can still compute this and do the same trick that we did, decompose with a micro-macro decomposition your f, and so you have L of G plus, LH of GH plus LH of MH. And so if you go back to the original variable, actually it's amounts to do, take your equation, so LH of GH is just LH of FH minus LH of MH, and we know that L of F equal to L of G, so actually what you need to do with your code is just at each time step to subtract the flux, your numerical fluxes or your numerical method applied to the equilibrium. And this is what we call this residual equilibrium. It's just this quantity. Each time step you subtract this quantity, which can be pre-computed because it's NH is constant in time. So you compute this once and for all, and at each time step you remove it from your solution.
And what remains of that if your t, for example, in your original equation is not constant?
If your what?
If the capital T in the Fokker-Planck equation is not a constant.
Oh yeah, so then the Gaussian becomes time dependent, and this is something we haven't tried, but I'm pretty sure it should work.
No,
because we need to compute this at it.
Because in the Shine-Cooper scheme, they do much more than that. In the Shine-Cooper scheme, they have all the parameters which are time and space dependent.
Yeah. But here we could do this. Oh no, because then we don't have a term here which we would.
No, because you need a global equilibrium to do that, and
yeah,
it's a huge implication.
Yeah, sure. But we could still couple because if your t is variables, you can still find an equation on t, and so by time differentiating the Maxwellian in this particular case, we can write the equation for because dmdt when rho u and t are time dependent, dmdt is just a combination of d rho dt, du dt, and the capital T dt. So we could still find an equation for the evolution of these quantities. Okay, so that's one of the way to improve this work is to make the equilibrium time dependent and see what happens. I agree. Well, anyway, so if you do this simple business here, what you can have, so it's a very simple 1D case. We start with the sum of two bulbs, and you would want to observe the convergence to equilibrium. So here I took 100 steps in space, so since it's parabolic, I took a parabolic step stepping, and I compare, so left is relative entropy, right is L1 error with respect to the equilibrium at each time, and so time evolution of this quantity, and for different scheme. So the blue dots are the Chern-Cooper, which is the best scheme we can have for the Fokker-Planck, and in particular the Chern-Cooper, so we can compute, so for example, we take the paper of Carrier and Toscani in 98, we can compute the rate of convergence of f minus m in M1 norm, so it's e to the minus qt, and the Chern-Cooper scheme is the only one which does the correct business to recover this rate of convergence. If you do, so these curves, this green curve and this blue curve are upwind scheme and central differences. So as I told you, it does a very bad business to recovering the equilibrium, as this thing just does not converge towards zero. But if you do our approach, that at each time you take a very simple either upwind or central, and you subtract the residual equilibrium at each time step, here what you obtain. So the red curve is if you do this with upwind, so instead of this you have this, which is not the correct rate, but still it converges to zero. So we do the dynamics here is not perfect because yeah, it's not the exact exponential damping. But if you do this with central, what is very nice is that you exactly recover the Chern-Cooper solution. just with a central scheme where you subtract at each time step the equilibrium. Very nice. You do a Chain-Cooper without the difficult implementation of Chain-Cooper. So we are very happy. So, as I told you, now we want to do this with more general problems. Again, some problems which have time-independent equilibrium. That's a limitation. So you have a general equation, the evolution problem of the form u equal to g of u, where g of u equal to 0 if and only if u is some kind of profile at u equilibrium, which depends on, okay, there is a t here, which should not be here. So the equilibrium profile should not depend upon time. And so you have your solver, which is an order Q approximation of the operator, so which we call the deriving method. And so this solver gives you an approximated problem, UH prime equal to GH of UH. And so, again, there's a T which should not be here. We can define a residual equilibrium like this. We just apply your scheme to your equilibrium. And again, time dependence here can be applied to the problem. And okay, since your method is of order Q, and so it's of order Q approximation of the equation, of course, when you apply by consistency, if you apply your solver to a profile which is hopefully smooth, what you will have is a remainder of order h to the q, because we want your method is of order Q, so this quantity will be small. If U is smooth, of course. And so now, as I did before for Fokker-Planck, you can define a new order Q approximation of your operator, because you just subtract something which is of order Q. By doing the same business, you subtract the residual equilibrium. And what you obtain now is a new scheme, which is UH prime equal to a mass calligraphic G, calligraphic G, H of UH. Right? Calligraphic G is just this difference. Again, you just modify your code by subtracting the residual equilibrium. So, one example is take your favorite parametric equation, nonlinear, by convection diffusion of the equation. So, for example, you can take Fokker-Planck for fermions or bosons, which is this equation with the drift, the quadratic drift, and linear diffusion. So what you obtain is one explicit equilibrium, which are this equation. You can also do this for porous medium, and actually I will show you simulation for porous media. So here the drift is linear, but it's the diffusion which is non-linear, and the equilibrium as per our pattern distribution. So let's see what happens when you consider this equation. So here simulation D equal to, so n equal to 5 for porous media in order to have strong nonlinearity. So 2D in space, so 2D I took 64 grid points. The initial condition is some kind of smooth. I mean, the profile is just it's here. Okay. But it's circular. I mean, it's a radial profile, and it has this kind of shape. Well, and we compare here in blue. It's an upwind method, so upwind from this paper, which does not preserve the large time behavior. It cannot resolve the pattern distribution. And we compare with the reference solution here is the one obtained with the so-called Scharfetter-Hummel scheme, which for this equation preserve also exactly the equilibrium, and also preserve, so we can compute the rate of, so this is relative entropy, this is L1 error, and actually we can compute also, again, paper of Karel and Doskanik, 99, we can compute the correct rate of convergence to equilibrium, which is e to the minus 5/9 for this particular set of parameters. And so here you have the reference solution was the scheme we found which can achieve this rate, and it's what was called free upwind by Desmoulins-Chattard and Fidley. So when we do, so this is the standard upwind, and this is our residual equilibrium upwind. So here we take this scheme and we remove the equilibrium at each time step. So we have the exponential decay to 0 of the relative entropy and error, but we don't have the correct rate of convergence here. So again, when we did it with Fokker-Planck, we could recover the correct rate by doing central scheme. Here my central scheme was not working at all, even without the residual business, so I couldn't achieve good accuracy. Okay, so here I have no explanation why we cannot observe the correct rate. I mean, I should choose a better underlying method. But it works. At least we converge to equilibrium, and the short time dynamics is correct, and okay, so in large time, we converge too fast. There's still room for improvement here, but it's just amount to choosing correctly your underlying method. Again, what a lot of people use is Schaffer-Gummel, and Schaffer-Gummel also doesn't achieve the correct rate of convergence. Okay, if we look at what happened point-wise, so this is the standard upwind, so time evolution, so initial conditions, so I'm trying to put the time evolution here, so it is, so here, and the red is a pointwise error, so between the numerical equilibrium and the theoretical equilibrium, so we see that upwind is very bad, it does not really reserve the correct variable distribution. Here is the reference solution obtained with the free upwind scheme, while Ferrara is very, sorry. Free upwind is here and our method is here. So just to tell you that we reserve a really we have a really nice resolution of the flat pattern distribution, but we use it on the scheme. So that's reassuring in some sense that we can sum we can obtain the correct equilibrium. So in 3D here is what happened. You have the correct 2D convergence to the pattern. In particular, here it's 0. Here it's 10 to the minus 16. So it's not just evolution, it's really not that we have it's a correct profile.
You rescale the domain when you get this, because the variable pattern solution it spreads and it's very small and
what gets, because when you take the positive part of this guy, so it's 0 and you have I mean, perhaps we can see it here, okay, you have 10 to the minus 11 everywhere, and then you have this. Right? But that pattern, it's not, it's localized, it's a compact support.
It grows, and becomes smaller with time.
Yeah, but this is if you consider the rescale. Here it's rescale. It's rescale. It's not Porous medium. It's not Porous medium here. Sorry, it's rescale Porous medium. Okay. Porous medium is just Tu equal to Laplace U to the n. Here it's dTu equal to Laplace U to the n plus the drift. So because it means that you rescale.
The very big problem when you compute on these things is to handle the fact that the domain should grow.
Yeah, but it's very easy.
Okay.
Once you know how to solve this equation, the rescaled one, you just change a variable in its post-process.
Yeah, okay, you do.
It's mostly
Scalia writes in his paper many times ago, but it doesn't change the basic problem of porous medium that, and filtration equations like that. But the domain, it should be very, very big because the whole thing is spread.
Yeah, but hopefully porous medium actually is self-similar, so you can rescale. But I agree that filtration, it's not self-similar. Yes, is it?
It is self-similar, but the problem is that it grows and you don't have an analytic expression.
Oh, okay, because, oh yes, so that's the problem. Because for porous medium, you have the analytic expression, so that's okay. But I agree with you. Here it's an ideal case because we have all the feature we want built in the model. But again, with this solver, we could do the real porous medium just by rescaling, and we have. Because we know the correct rate, actually, it's also in the paper of Toscani and Cario, so we can compute it. But yeah, I agree. It's not perfect, but it's not the real equation. Perhaps I should have shown you the simulation for the Fermat-Dirac case, which here is a true equation. It's not a rescaled version. Okay, so we can do the same for Boltzmann. It's the same business. You take the Boltzmann equation, so quadratic nonlinearity. So just to remind you, so here it's homogeneous Boltzmann. So you drop the transport part, and you have the FDT equal Q of F, where Q of F, the Bayesian operator, characterizes a particular interaction. So we already saw this in many talks. So here is the usual strong form of the Bayesian operator. You have a difference between, again, a bit between the gain part and the loss part. So the gain part, they use the probability to obtain a particular velocity v prime and v prime star after a collision of two particular velocity v and v star. And here is the collision dynamics, here it's elastic. And you have a collision kernel, which is not exactly a probability distribution because it's not integrable, but it has somehow like a probability of collision between two particular velocity, relative velocity v minus v star, and the collision angle n. Okay, but here what is important for this talk is that the equilibrium states are again described by Gaussian distribution. And so we can do the same business. You have, if you have a solver for this equation, you remove the residual equilibrium by applying your method to the global equilibrium at H that you project on your grid. And again, you can relate this to the micro-macro decomposition because in that case, because you have a quadratic nonlinearity, actually if you look at the equation on G, if you do the micro-macro decomposition, what you obtain is this. There's a linear part, which depends on GH and H, plus a quadratic remainder, which only depends on GH. And in the Boltzmann world, usually this guy is okay, you can load it in the correct norm, and then if you want to do analysis, you need to look at the property of this operator, which is manageable. But okay, but the point is here again, since G has zero mass, momentum, and kinetic energy, the equilibrium of this solution are GH equal to 0, which is good because now in any space of reconstruction of your solution, usually you will resolve the constant. So here we did it with the spectral method because we want to use a very, very high order method. Here it's infinite order in some sense. So we do the same business, so there's your spectral, so we have this equation on G, and so here since it's spectral, we project on the space of trigonometric polynomial of degree n, so Gn is just projection of G, Mn is projection on n on this, and Ln and Qn are the projection of the operator. And again, thanks to the micro-macro decomposition, even if M, which is a Gaussian, and so does not live in the space of trigonometric polynomial of degree n, so it's not resolved by the method, while G, which is a constant, it belongs to the space Pn of orthogonal polynomial, so it resolves the correct, so the scheme here will resolve the correct equilibrium, and then we reconstruct F by just doing M plus G. So and so Fn is Mn is the local equilibrium state. Okay, so we can prove. So we did this in the note last year. No, actually, it appeared this year. But anyway. They're doing just this modification does not change the property of the method because we have this lemma, which is very classic for some of you who know about spectral method for Boltzmann, that the method is of infinite order on the Gaussian. You have this estimate, you just take the Fourier sum and you do your business. So if M is in HR, then the method is of order R minus 2, but since M is a Gaussian, it's in infinity. So here you can just R and you have this estimate on Qn of Mn. And so you can prove that the error you do when you compare Q of F with the residual equilibrium scheme, which is Ln of G minus Qn of G, what you obtain is something which is C on N divided by R, where R is the regularity of your solution. So if you deal with smooth solutions, the method is of infinite order. And so actually, so the method is the order of the method is given by the order of the solution. So you can still have good stability property for doing so. So you don't lose the property of the method for spectrum. Okay, so here is what happens. So here I'm not computing the rate of convergence to the Gaussian, but the error with respect to an explicit solution, which is more usually done for Boltzmann. And so with the classical spectral method, what you obtain is that in small times, that's okay, you have a correct error, but then your method, since it does not resolve the maximum properly, your method starts to do strange stuff, and okay, with our modification, we preserve the small time behavior of the method, but we converge also to the correct solution. Okay, so we have some bursts of positivity here, which we can observe on the relative entropy, but it's not a very big deal. Just some cells which do some strange stuff that still need to investigate. So here it's 2D velocity. Okay, but okay, so since it's hyperbolic, the workshop is intended for hyperbolic balance. Here is a test case for shallow water. So at first, when we did this work, it was really new in well-balanced business, and okay, I never worked on this type of equation, so I had to learn it fast. So perhaps if I will say something wrong, so don't hesitate to tell me. So here we just did the 1D shallow water with bottom. So okay, here G is the gravitational constant, B is the bottom profile, H is the water height. I mean H plus B is the water height, and U is the water velocity. And again, since in our method we need to know the equilibrium profile, here with this equation, usually you can compute the state just by equating the fluxes to zero. So just you need to write this in another form, but you can do it. And okay, so the steady-state solution, our solution to this system of nonlinear equation where the constants are determined by the boundary condition. Okay, so we can do this, and so here is an example. So since I was new to the business, I didn't use the good schemes for the equation. So I just took my favorite Lax-Friedrichs method, so central, with the flux limiter, in order to have an order 2 method at least. And this method is new to be able not to, but it does not preserve the equilibrium of this equation. And so it was a good test, so it's high order, but not AP, let's say. And we wanted to compare with the residual equilibrium version, where we just subtract the equilibrium. So here, a very easy test case, perturbation of a lake at rest. So you take a bump on the, you can view the sandpipe, for example, at the bottom of the water, and you just perturb a little bit your lake at rest. And the equilibrium, of course, is the lake unperturbed. So here is what happened. Here we need, perhaps go back. So left is water height. So the green here is the bottom. So the blue curve, and the red curve is the Lax-Friedrich solution. The blue curve is the residual equilibrium Lax-Friedrich solution. So the reference solution that I computed was 2,000 points. Okay, B is the bottom, and here both Lax-Friedrich and residual equilibrium are computed with 50 points, 100 points. So here is what happened, and I want to emphasize here. So the Lax-Friedrich solution is bad. It's very far from the real profile. There's too much damping. The shock is not correctly resolved here. The contact discontinuity, but it's not resolved properly. But so even in short time, our residual equilibrium method, so that we obtain by subtracting the equilibrium, it does a pretty good job. Even if the grid is very coarse, we are still able to compute with a good accuracy. It's much closer to the real solution. Here, we don't have this spurious oscillation, and even if it's the same scheme here, the underlying method is the same, but by subtracting the equilibrium, you keep this spurious oscillation. And so, okay, and if you let time evolve, everything will stabilize. And as you can see, Lax-Friedrich does a very bad job with this oscillation that we still have a little bit in the residual equilibrium version. No? But still, if you look at the water height, so blue here is equilibrium. So we are still very close to the equilibrium, especially compared with the Lax-Friedrich solution. Okay, and if we look at the error, so I know that for this model there is no convergence. I cannot prove any convergence to the. And there's no rate of convergence actually. And so if we do Lax-Friedrichs by taking one more point, of course we will converge. So this is the L1 error on the water height with respect to the equilibrium. So Lax-Friedrichs will converge, but at a very low rate with our method. So the transient behavior here, okay, so it happens, but at normal it's not converging in short time and in large time. Well, it does not a bad job. It does, the error is not that good, but it's still better than the underlying method. Here again, it's a very basic numerical method. I know that there are much better methods for shallow water, but still. And so we are still very happy with this, but actually there was one problem. I told you, if you want to preserve the order of accuracy of your method, if you have a method of order Q, the residual will be of order Q, if the profile is smooth. If the equilibrium, but if you have a shock in the equilibrium profile, I mean, you won't expect the residual equilibrium that you will subtract to be small, and then the modification you do to your scheme is big, and you lose the order of accuracy of your scheme. So here is a case where this happens. So here we take a transcritical flow, and this particular test. So you take a smooth bottom, and you put an inflow on of water, and you will have a shock after the bottom, after the bump on the bottom. And so the equilibrium has a shock. So, oh yeah, sorry. Just to show you, well, so we have spurious oscillation. Just to show you this. Short time, okay. So here we see spurious oscillation on the residual equilibrium method, which are not good. So just to talk about this, just 30 seconds. So this was bad, but actually it can be improved. So by doing a flux limiting approach. Actually, so since the residual equilibrium can be big, so let's take a limiter. So it's just my final word is let's find a limiter which is small when the equilibrium is small, when you're far from equilibrium, because the dynamics in short time usually, if you have a good scheme with good property of preservation and TBD, well, the short time the dynamics will be good. So let's take a limiter which will be 0, close to 0 if you're far from equilibrium, and close to 1 if you're close to equilibrium, and then just change your method like this. Instead of subtracting the residual equilibrium, you subtract it with a coefficient. You do really a flux limiting business. And okay, so just to tell you, with the same test case but with limiter, well, you don't have the spurious oscillation. Still a little bit, but much less than before. And because you damp the problem. And at the end, you converge toward the good rate. And just to show you the rate of convergence for this particular test is very funny, because it seems that we have some kind of, I don't know, we have the envelope of the, so this is the error of the water height with respect to the equilibrium profile, and it seems that we have, I don't know the theory here, but it looks like what you observe with Boltzmann, because there's some kind of acoustic wave, or I don't know, I would like to discuss with somebody new why we have this, but just to show you that flux limiting improves. So this is a non-flux limited with equilibrium. So this is like Friedrichs with theory, this is residual equilibrium, like Friedrichs, and then the flux limited version, which does a much better job to have the convergence to the equilibrium profile. Okay, we'll stop this and we'll say thank you. That's it.
Lunchtime, but perhaps one or two questions.
You thought about the preservation and gradient flow structure. Means that you also, in the case of something in a gradient flow, which is a gradient flow or something, you mean that you have to preserve. In that case, the equilibrium is the minimum of a functional energy related to the equation.
Yeah.
Right?
Yeah, exactly. And so it could apply to this method, because if you have a way to complete the equilibrium, so by solving the minimization problem, then you could plug what you obtain in your method, which is not designed to preserve the gradient flow structure, but at the end, the method, I mean, at least the numerical evidence we have tells us that it should give you a method which will preserve the large time behavior, because you built the gradient flow structure in the equilibrium, and you built it in the scheme, because you subtract. I mean, that's my point of view on the equation. But you don't have to preserve the gradient flow to solve it with the correct norm or whatever. So, perhaps I don't know. It's really linearly here. That's an idea.
There are no more questions. Let's thank the speaker and